Welcome to Maths 420. We're now in the second part of chapter 1. Again, like we had heard earlier on in the first part of it, everything we're going to be learning is using basically matrices to understand finite groups. So we're going to the next question. I believe you're now conversant with the basic definitions and properties needed thus far. So the next question is actually theorem 1.10, that's theorem 1.10 in your lecture notes. And it says if AX is a representation, now you know what a representation is. It means that we have AXY, that is AX, the matrix satisfies this condition, AY, okay? So that's what we mean by a representation, okay? So if AX is a representation and this Bx, another matrix representation, is a representation of G. Note, we had defined something like this when we said it was equivalent. If you remember in the part 1, you can go over the slides or the lecture notes to find out and compare notes, okay? Where T is any fixed non-singular matrix with coefficient in the field K. We're to show that this particular conditions all hold, the three of them. So now we know that Bx has this, and we know what A is, okay? And we're trying to show, based on this information of Bx and A, that these conditions are satisfied. So what do? Now you have the different conditions attached to the matrix, okay? So let's see the solution. So now we know what Bx is, it's this. So we only need to prove the three properties. So we consider the property for Bx, that is, that it is a representation, okay? So what do? Now what is Bx? Bx we know is going to be, Bxy is going to be this. Why? Because we know that Bx is equal to T inverse Ax T, right? So wherever you see x, you put xy. And wherever you see x, you put xy. I'm sure you're used to this by now from part 1 of the lecture notes or chapter, okay? The video thus far. Okay, so we know how we got this already because we know AXY is a representation. So it satisfies these conditions. Wherever you see AX, you put AXY, you put AY. And this condition holds because we can simply put this in between because it is what is taken in non-singular matrix, okay? So it satisfies this, okay? So it means that this is equal to this. You have seen this proof earlier on in one of the questions previously solved, okay? So we've succeeded in showing that Bxy satisfy Bx times By in its block form. Okay, so it satisfies that in its block form. So it means that if I substitute wherever I see, remember what Bx is. Bx is actually this equation here. So we are now looking for Bxy, meaning that wherever there was x, you just put xy, xy, right? Okay, so let's see what we've done. So exactly that, you can see for Bx on your left hand side, wherever there was Bx, xy, you put the xy, and 0 remained 0, okay? On your right hand side now, so on your right hand side, which is what we've proven that this is equal to this. So in its equation form, it looks like this, right? And so in matrix form, it's this, and your right hand side takes on the equation for Ax and for Tay, basically using this ones here. And there are 2 of them. Okay, so therefore we have for x and we have for y, remember? Because the other one is in x and the other one is in y. Okay, so with that, you have this relationship. So all you need to do, there's nothing to do there's nothing to do on the left hand side here, but you need to multiply this out. Earlier on in chapter 1, we had shown how to multiply for a 2 by 2, if you remember. We showed this, and we saw the short formula, the equation in the sum form, if you remember, if you're doing A times B, and it looks like this. Okay, so by now you should know the formula by heart. So all you need to know is compare notes. So this is going to be my A11, right? This 0 is now my A12. EX is my A21. DX is my A22. And so also for CY, like that. 0 is my B12. EY is my B21. And DY is my B22. Okay, so you can now compare notes now that you know which one is which, and substitute for each of those values for the first term, and you'll get this. Second term, you should get this. Like that, each entry should give you the entries you see right here. Okay, so you can verify. You can pause the video, solve yours, and see if your multiplication would look as you can see up to this point. Okay. Simplifying further, you can see that this plus 0 is just simply this is that, and this plus 0 plus 0 is 0, and this term remains just as it is, and 0 plus this is just going to give us this. So that's how we arrived at this value here. Okay, so all you need to do is remember your multiplication for a 2 by 2 matrix. Okay, so we found that the multiplication is going to give us all of this. Okay, so let's compare notes. So we know what BXY is. It is this, and the right hand side was this, right? So if you equate them, so you remember when we say two matrices are equivalent, it means that the entries, respective entries, are the same, right? Or they are equal. So 0 will be equal to 0, EXY will be equal to EX, all of this, right? Yes, because these two are the same, and DXY is all of this, right? So let's check now. So equating the two, let's see if our lecture, the slide and the lecture notes tallies. Okay, so CXY is this. Exactly, we've gotten that. EXY, oh sorry, we're supposed to do DXY before EXY, right? Okay, so we'll do DXY, right? So DXY is going to be the term here, right? Satisfies that. And finally, we're looking for EXY. EXY is all of this. So let's check, confirmed, and that completes the proof. Okay, so if you're asked to, let's go back quickly to the question itself. So if you're asked to, so if you are given matrix representation of this form, and it's reduced form, and you're told to show that these conditions are satisfied, then you just simply do as we've seen in explanation on the slide thus far. Okay, you can try again, like I said, pause and make your attempt on your own. We'll go to the next question. The next question is question 3, actually theorem 1.12 in your lecture notes. It says, given that AX, okay, is a matrix representation of G and is of degree M over the field K, show that AX is irreducible, or else it is of this form. So if it's either it is irreducible or it will take this form. Okay, so what do we do? How do we do? To be irreducible, and this will be the values. The AIs will be irreducible over K. So that's all of the entries on your diagonal here. You can see them. They are irreducible. Okay, so let's continue. So solution, which is our proof for that particular theorem, says let AX be a matrix representation of G over degree M over K. So what do we want to show? We want to show that either A is irreducible or it is that block diagonal form as we saw earlier on. So we have two cases before us, okay? The first case will be when m is equal to 1. Once m is equal to 1, let's see what happens on the previous side. Once m is equal to 1, all you just have is just the first entry, right? It'll just be all of this. So that's all. We're through with it. So it's a simple case. So m equals 1, ax is irreducible. Therefore, we are done. So the next case is what happens if m is greater than 1. So if m is 2, we'll just have this simple case, the second case, right? Because when it is 1, it's simply that particular one, right? But now it is 2, so to just take the form of this t equals a x t, okay? And this one will be irreducible. But then dx, we don't know if it is irreducible. So if dx is irreducible, then we're done with I equals to 2, okay? Sorry, L equals to 2, because like you saw in the diagonal here, we stopped at L, okay, right? Okay, so we have two cases, m equal to 1. The second case is if it is greater than 1. So if it's greater than 1, we consider m equal to 2. If m equal to 2, we'll get this matrix, which is actually bx, but not exactly bx because now we're working with a1 in the first entry there, okay? So if this will stop if dx were to be irreducible, but if it's not, then what happens? It means that dx will be reducible. And continue inductively with m, we just set the dimension of a1, so a1 is up here, right, to be equal to r, and the dimension of dx to be equal to s, okay, based on our definition of our matrices from the original question, right? Okay, so we will just have to have this particular kind of matrix, because if you note, whenever we are relating A to B, we would always have a non-singular matrix of this form T, right? Okay, so we will know over time inductively. If you note, A1 just comes in based on the matrix that we are assuming it will become at the long run. When we got A1, we got that one of a 2 by 2, and these two were in terms of a bx, if you note, okay, and this was dx, okay, this was cx, okay. Okay, so with that said, we know this particular one, which was dx, became reducible. That's why we're extending our solution. So we're going to extend it over m. We'll have something in this form because we know this is already irreducible, so we don't know. We want to work with this part of it, okay? So working with that part of it, let's see what we get. So we have something like this, right? You can compare the two matrices and see, and that is because we have a non-singular matrix of this form. Okay, so we don't know what this is. We don't. We always need it when forming our A, okay? So we only need to show that this condition is going to give us this. But how do I know this? So we claim that this thing is actually going to be true. So let's prove the claim. Your question would be, how do you know this? Well, the person that did the research had solved and had seen that when he or she used this particular formula, it worked. So let's see if that is true. So we use our claim. So our claim is that this will be true on the condition that if we set S to be equal to this particular matrix with entries of this form, where I is the unit matrix of degree R, and we know T equals AXT. So all we need to find now is what? Is S inverse, okay? So now we want to solve this and show it is equal to this. We have said S is going to be, so we know what S is. S is this value. We know T inverse TA, so we just need S inverse. So S inverse, standard rule of matrices, is that once you're given these values, S inverse will definitely become I with the entry 0, 0 and 0 not inverse here. Why? Because the entries are matrices, and also I inverse is the same as I, okay? So note that, okay? Okay, still making, let's claim this. So I'll take it again. We started by saying that we're working inductively on the order of m, right? So we started with m when it is 1, and we saw that we'll just get a 1. So it was irreducible. But if m is greater than 1, we then have a 2 by 2 matrix in such a way that it is just like Bx itself, with D possibly reducible or irreducible. So if it is reducible, if it is irreducible, then we're done. But if it is reducible, we have a situation there. And when we have such a situation, we know we're going to be working with an m that is actually big. So with that, let's assume that our D satisfies this particular form and satisfies this particular type of matrix based on the given target of matrix that we're working with or targeting to solve. Okay, so we have chosen what we want our D to look like in its reduced form. Okay, so and then we claim that if we take S inverse of T inverse A of XTS, that will be equal to this. And we began to prove that by setting S to be equal to this. That's because we already know T inverse AXT, but we didn't know S. So we set S to be this and see if it will work. We just assume the values. Over time, over practice, the persons that solved discovered that this would work for S. But let's see if that would be true. So we need to find S inverse. And I can explain to you the standard laws of matrices. When finding S inverse will give you this. You can verify that with your previous knowledge of matrices. Okay, so now we found S. So we've chosen set S to be the value we want. We know T inverse AXT, and we found S inverse. So let's find out what will happen if we multiply out this, whether we'll get the solution on our right hand side. Okay, so we need to find S inverse T inverse AXT, right? Because that's the first thing. We have to multiply this together first. That's within here without the S. So we need to find this part first, and then later we'll multiply with the S matrix. So S inverse T inverse AXT, S inverse is this, and T inverse AX is this. So using that same formula we had used before, we know what I will be A11, 0 is A12, this 0 is A21, S naught inverse is A22, and A1X is B11, 0 is B12, EX is B21, and DX is B22. Okay, so if you substitute it back into the rule for the multiplication of y 2 by 2, it's expected that when you substitute and multiply it carefully, you substitute the values, you should get what you have here. Noting that A11 is your 1, is that? Let me get it back. A11 is I, not 1, sorry. A11 is your I, and B11 is located here. It's your A1X, so you can see what we have here. So you can pause the video, try yours, and ensure that the values tally with what you have here. And then you simplify. 0 times dx would just be 0, and then you have I times A1 will give you A1. And all of this goes to 0 because 0 times anything is 0, and the sum of 0 plus 0 is 0. Also for this, you just be left with this term because all of this goes to 0. This is 0, and you're left with just S inverse dx, which is what you S naught inverse dx, which is what you have here. Okay, I might have been fast there, or I am fast. So what I want you to do is to pause the video, do your multiplication, and compare and contrast whatever you get with what I have gotten. Okay, so we've succeeded in showing the multiplication for S inverse T inverse AXT, which is right here. Okay, so let's see what happens now when we multiply by S. So we found all of here. We're now multiplying by S, and this is S, right? This was found, and I'm sure you've confirmed the italics. Okay, so if we multiply using the same formula, so here I've written a general formula because by now I'm sure you've got English straight. Same procedure, just substitute. Now compare, substitute like we did before, noting that this is your A11, this is your B11, and then substitute. Okay, substitute, simplify, and multiply, and then let me know on the WhatsApp if you have issues with the multiplication. After multiplying, you should get these values at the long run. Okay, so pause the video, do your multiplications, and show your workings. Okay, during the exams, I expect you to show your workings. For me, all I have done is to present it as a lecture note. Okay, so the proof is complete simply by substituting these values. So now I have done a screenshot here. This is the expected thing we're substituting back. We know what a1x is already irreducible. 0 remains 0. And this particular part of the matrix is all of this here. So you want to plug this big thing right here, right? It's going to be a big one. And then this one is a column vector. So it takes all of here. Okay? So by the time you put them pictorially back, you should get what we were looking for in the starting of the question. That is what we have here. Now is it here? Right here. So we have here, we have a column vector, and you have the other value S naught. Is it S naught? So we have the column vector, see S naught. I'll get to it. So we want to get the column vector S naught inverse. Okay, let's go back here. So by the time you substitute, you get exactly what we have here, S naught inverse dx, right? So which is what we have here. So you could just pause the video, run over the entries again, do your sums, do your calculations, I meant to say multiplications, and compare and contrast results. And with that, we are done with the proof of that particular theorem. Okay. So next is the theorem 1.12, which I have also framed as a question here. It says, show that if AX is a matrix representation of G, now you know what a matrix representation is, then so is the contragradient representation. So if you're asked what is a contragradient representation, we mean this term here. A contragradient representation is AX inverse, which is equals to A transpose of X inverse. Okay, that's a contragradient representation. So what the question is saying is that you should show that the matrix representation AX, show that if this is the matrix representation, then so is the contragradient representation this. Whenever this is a matrix representation, so also is this. Okay, and T denotes the transposition. So let's see how we do that. All we need to do is show that so based on this, all we want to show is that AX, okay, well, if I want to show this a representation, I actually need Y, right? AXY inverse is going to give me X inverse Y inverse. That's what it's going to be as our target. Okay, so let's see how we're going about it in the proof here. Okay, so the proof says let AX be a matrix representation of G over the field K. We want to show that the contragradient, so you see the notation's a little different here, but it all means the same thing, is also a matrix representation of G. And we just noted here that this also happens, that if you have the A prime prime X of it, it's going to give you back the matrix representation AX itself. Okay, so let's continue now. Okay, so now we recall that for AX to be a matrix representation, it must satisfy this function, this homomorphism, right? And so we want to show that this thing will be equal to this. That's our target. So, well, basically we want to show that this thing will give us this, actually. So let's see how we'll go about it. So solving it step by step. So A prime X, A prime Y is the same thing as this here times this. Do you agree? That's because let me copy it here. That's because notation all the way. I would have written A prime of x for you here to be equals to A x inverse. That will not get us confused. That's the A transpose of x inverse. They're all the same thing, okay? When you see A prime, note that. That's what I'm meaning this, okay? Let's work with it now. Okay, so now back to the solution. We want to show that it satisfies the condition of a matrix representation. So A prime x, A prime y, we know A prime x is A transpose of x inverse. We know that A prime y is A transpose of y inverse. Agreed? Now, because A, B transpose is the same as taking an individual transpose of A and B transpose itself, the transpose of AX inverse is the same thing. Watch, you have A transpose of this. The transpose are individually here, which means I can write all of them under one transpose, which is what we've done here. Are you seeing that? Okay, they were individual here, so individual on both sides here, and they can be written together as one. That's how we got all of them under the one transpose there. Okay, so let's continue now. So this came from the definition, and this next step came from the rule here. Now if you have single of it, you can bring them under one transpose. Now this AY inverse and AX inverse can be written this way. Reason because AX is a matrix representation. Matrix representation says A, okay, I don't even need to write it up here, right here. Based on the matrix representation, this matrix representation allows me to write this as this, okay? And I believe you already know that once you see y inverse, x inverse, it's the same as xy all inverse, okay? And the transpose keeps following quietly. That's because of, and this is because of this rule, okay? Now, but then, whenever we have A, X with transpose, or all over it's everything transposed, we know it's the same thing as the individual transpose, right? This is same as saying A prime of X, right? Okay, so that followed this last step here is coming from the fact that I can write this transpose over all as bit of it. Is that not so? So I could write it as what you see here, okay? And what is this? If this were to be X, all of this, let me just put its dot in between, it'll be this dot. Is that not so? Look at it from the definition here. Whenever I have X, it is just this. So if I have XY, it will be A prime XY, okay? So therefore, we have succeeded in showing that A prime X satisfies the group homomorphism property and is therefore a matrix representation of G. So the contragradient is also a matrix representation of G. Okay, if my explanation is not so clear and you have issues, just ask on the WhatsApp, okay, and the group. So carefully go through it, study it, and ask your questions. Thank you.